Okay, so this talk is called Sums of Lattice Points, Ordered Groups, and the Hahn embedding theorem. So there are three topics, two of which I know very little about. So let me just review what I talked about 2 weeks ago, which sets the stage for this. So n is the positive integers, n0 is the non-negative integers. If you have any set A of integers, this counting function A of n counts the number of integers in A, positive integers in A, no greater than n. And then what is called the Schnirelmann density is the imp, not the limit, that would be the lower asymptotic density, but simply the greatest lower bound of A of n over n. And an equivalent way to write this, because it's analogous to what I'm going to show in a minute or two, is that this is a script J. So that script J be the set of all intervals of integers 1 through n. So I can also write this as the Schnirelmann density is the imp of, you look at A intersect, the number of elements in A intersect J divided by the size of J for all these intervals. So this gives us a density which is between 0 and 1. As everyone observes, it's a strange density because were you to take the set consisting of every positive integer except 2, in the just world, that would have density 1, but the Schnirelmann density is 0, because 1's not in the set. So what is the very famous and beautiful inequality of Schnirelmann from a paper in 1930 in a somewhat obscure Soviet journal at the time, says the following. If you have two sets of integers A and B, both containing 0, if alpha is the Schnirelmann density of A and beta is the Schnirelmann density of B, then if you look at the sum set A plus B, this means every integer that you can write in the form little a plus little b, where the first summand is from the set A and the second summand is from the set B, that's greater than or equal to alpha plus beta minus alpha beta. And just to check the obvious thing, if you look at alpha plus beta minus alpha beta, that's at most 1. So there's no, it's not like there's some weird choice of alpha and beta, this is bigger than 1 and the inequality doesn't make sense. This is always at most 1. So that's Schnirelmann's inequality. And this led to the first, together with the Brunn sieve, which before Schnirelmann, practically no one understood except Schnirelmann and Brunn, the first non-trivial result on the Goldbach conjecture. So if you take Schnirelmann's inequality, you can rewrite it slightly like this. So 1 minus sigma of A plus B is bounded above by 1 minus alpha times 1 minus beta. And you can iterate this for sums of H different sets of integers. So you have sets A1 up to AH, and sigma of AI is, the Schnirelmann density is alpha I. So A1 up to AH, this is the set of sums, all integers that can be represented in at least one way as a sum of one element chosen from each of these sets. So 1 minus the density of the sum set is less than or equal to this product. And if you take all of the sets AI to be the same set A with density alpha, this says 1 minus sigma of HA is at most 1 minus alpha to the H, or the Schnirelmann density of the H-fold sum of a set is bounded below by this quantity. And if the density of the set A is positive, if alpha is greater than 0, then 1 minus alpha is at least 0, but strictly less than 1. So if you take higher and higher powers, this goes to 0. So for some H0, the Schnirelmann density of the H0 fold sum set is bigger than a half. And then a pigeonhole principle argument tells you that if you have a set whose density, whose Schnirelmann density is bigger 1/2, and you add that to itself, you end up with a set of Schnirelmann density 1, which means every integer is in this sum set. So you have the H0-fold sum set. When you add that set to itself, you have the 2H0-fold sum set, and that's the basis. So this really is, this is a brilliant observation. It says, if you have any set of integers of positive Schnellmann density, then it's a basis for the set of non-negative integers. A basis means that every non-negative integer is a sum of a bounded number of terms from the sequence. And what Schnellmann did was, using the Brun sieve, the primes have Schnellmann density 0, but he proved that if you take the primes and add them to themselves enough times and throw in 1, you get a set of positive Schnellmann density, which implies that every integer is a sum of a bounded number of primes. This was a spectacular result. So this is a result about integers. And in my talk 2 weeks ago, I said it would be interesting if you could extend the Schnellmann's inequality and Schnellmann's theorem to the sets of non-negative lattice points. So n0 to the d for d greater than or equal to 2. And what I said at the time was, as far as I knew, this was an open problem. There's no proof of this. So as some people know, I'm in the habit of writing things down and putting them on my computer where they sit forever. And I happened to be looking at some notes I had written on Schnellmann density about 10 years ago. And lo and behold, I actually found a proof of this result about lattice points. But these were really notes. So I have no idea where the proof came from. I mean, it's 10 years old. I mean, maybe I proved it. Maybe I saw it in the literature somewhere and just wrote it down to make sure that I understood it. But I know that in the various papers on sort of like in the limited literature that I know on sums of lattice points, I don't think this is there. But it doesn't mean it wasn't somewhere else. So
you think at the time you didn't try and publish it?
No, I have all this. No, I mean, I have all this crap on my computer. I also thought when I looked at this that somehow it was connected to another subject I know nothing about, which is ordered groups. But then I found from 2010 some notes I had written down on ordered groups, and at the beginning, I had put a little note to myself, which is include Hahn's Hahn's embedding theorem. It's the same Hahn's from the Hahn-Banach theorem, and so I had no idea what this theorem was, but I mean I sort of spent a week trying to understand the statement of it, which is sort of what I'm going to talk about right now. So the upshot is, I hope, as I said, this is like not really like a proof written down yet. I mean, partially, but who knows? This theorem about lattice points is true, but it's actually true in a much wider sense in the context of ordered abelian groups, torsion-free, ordered torsion-free abelian groups. Okay, so let's begin to talk about that. So, all right. Now, I should say, when I asked about Schnellmann density for lattice points, what does it mean? I mean, it means you have, like for the integers, you have the intervals from 1 to n, and you have a set A, and you look at the intersection, or a set, you have a set A, and for the integers, I took J to be the interval from 1 to n, and I looked at the size of A intersect J divided by the size of J. So for lattice points, how do you define Schnellmann density? So there's a kind of general definition you might give of Schnellmann density, which is the following. So let X be an additive abelian group or semigroup, and that J be some set of non-empty finite subsets of X, where the union of all the J's is equal to X. So for every subset A of X, given this collection of sets J, we can define a Schnirelmann density, a Schnirelmann density depending on J, sigma J of A. It's the inf of A intersect J, size of that over the size of J for all these sets. Right? So that's like, you might say that's an abstract definition of Schnirelmann density, but given a set X, it's defined for any collection of finite sets whose union is X. So you have as many different Schnirelmann densities as your imagination gives you collections of sets, right? I mean, you might ask for a collection of sets that's reasonable in some, sense, whatever that means, but who knows? So the general problem you might ask is, for what pairs XJ do Schnirelmann's inequality and Schnirelmann's theorem hold, right? As far as I know, it's actually a new question because.
Would you want to connect this to measure, the stuff like on Fulner sets from amenable groups?
So the other topic I said I would talk about in due course has to do with sums of, you take a group, a locally compact, let's say locally compact abelian to make it easy. And you look at Hahn measure of sets, and you look at the Hahn measure of some sets and ask how that relates to the Hahn measure of the sets. But that's sort of like a continuous version of all this. And today I'm just talking about discrete problems. So, I mean, there's a whole
Fulner sets are discrete things, though.
Excuse me?
Fulner sets are discrete things. You
can use
it for. So would you want to? I mean, do you think there's any use to restricting this J to Fulner sets?
Use?
Sets? What? Yeah, I mean, for example,
if you do that and prove a nice theorem, the answer is yes.
Okay, so would it be helpful here to know that the sort of a small boundary J has a small boundary compared to its size?
This is all.
That's not a sum set. What?
This is all new to me and like a terra incognita, if you like. I mean, the literature on discrete amenable groups and Fulner sets and so forth in this context is huge to begin with. I mean, there's, yeah. Anyway, I'm just dealing with something very simple. First of all, because the word abelian is here, which just means it's very simple. So the question is, for what pairs, sets X and collections of sets J, do Schnirelmann's inequality and Schnirelmann's theorem hold? So if we take the sum of sets of lattice points, n-dimensional lattice points with non-negative coordinates, so there are two well-known ways to order this semigroup, whether you take the whole group of n-dimensional lattice points or the semigroup of n-dimensional non-negative lattice points. I don't know what the name of this is, but you take X and Y, and if each coordinate Xi is less than or equal to the coordinate Yi, you have a partial order. For everything in the non-negative octant, everything is bounded below by the zero vector. It's not a total order. For example, if you take the unit vectors in each direction, they're pairwise incomparable. But it's a nice order. Now, for this semigroup, you look at, let's say, the semigroup of non-zero lattice points with non-negative coordinates. One choice of your test sets J would be the downward closed finite non-empty subsets. They're just finite sets with the property that if Y is in a set J and X is less than or equal to Y, and in this set, then X is in J. And you could use this set JD, D dimension X, to define a Schnirelmann density on the non-negative lattice points. People have looked at this and proved some results going back a long time. This is what one usually chooses. as your set J. I should say, there's nothing special about this set, the choice of these sets of downward closed sets, except that they're nice and you can prove theorems about it, but it's one choice out of many. I mean, you could choose truncated cones or disks or whatever you like, because as I said earlier, for any collection of sets, JD, finite non-empty sets whose union is your whole semigroup, there's some associated Snell Nathanson. But this is in some sense, the classical choice. Now, on this group of lattice points, or the group of non-negative lattice points, in addition to the partial order I just described, there is a total order, lexicographical order. You take two vectors and you say x is less than or equal to y lexicographically if either the two vectors are the same, or you start comparing coordinates, and if I naught is the smallest integer for which the coordinate xi naught is different from yi naught, then if xi naught is smaller than yi naught, x is less than y. So with this total order, and if you take the unit vectors, you have an increasing chain like this. So this is a total order. And it's worth pointing out, actually it's important to point out, that this total order extends the partial order, in the sense that if x is less than or equal to y with the partial order, then x is less than or equal to y with the lexicographical order. And there's actually a beautiful theorem by Spielrein from 1930, which says that this is not like an oddity. If you have any partial order on a set X, it can always be extended to a total order. It's not completely trivial to prove that. I mean, they're nice. Today, they're nice proofs, but I think this at the time was a hard theorem to prove. And it's not obvious.
I mean, doesn't the Spielrein theorem require, I mean, it doesn't make any assumptions about the underlying operations. So, I mean, Spielrein's theorem is comparatively easier to demonstrate, right? I mean, it's...
Well, I mean, I'm not sure what you're asking or saying, but I mean, this is a statement of Spielrein's theorem. I mean, there may be other versions of it, but it just says that a partial order can always be extended in at least one way.
But there's a lattice structure here.
Excuse me?
There's a lattice structure and a semi-group structure, which is essential. In this case.
Well, the set X doesn't have to be a semigroup. It's just a set X that's partially ordered.
Okay, sure. There's an extension, and so yeah, okay, sure.
Well, when you have a group or a semigroup, it may or may not be ordered in some sense. So if G is an additive abelian group with identity 0, with a total order, we say this is an ordered group if whenever A is less than B, for every C, A plus C, this should be a C here, A plus C is less than B plus C. And if you have an ordered group, and this is a total order, you can let S plus be everything greater than 0, S minus everything less than 0. These are both semigroups, and in fact, you have a partition of the group G into the positive element, 0, and the negative elements. And that, in some sense, characterizes ordered abelian groups. If you have any partition of G as a union, as a disjoint union of two semigroups and the identity, that defines an ordering on the group, right? So you say that A is less than B if B minus A is positive. So being able to partition a group into a union of two semigroups in the identity is equivalent to the group being what we call orderable. Right? So G is orderable if there's a total order on the group that makes this an ordered group. And it's easy to check that every ordered group is torsion free. Here I'm just writing it multiplicatively for some reason. This is true for non-abelian groups. If A is greater than the identity and you multiply this inequality by A, then you get A is less than A squared. And if you keep multiplying by A, you get the strictly increasing sequence of group elements. So in particular, you never get the identity. So in an ordered group, every non-identity element has infinite order. And it's also true, this is a tad more work, that every torsion-free abelian group is orderable. So being torsion for abelian groups, torsion-free is the same as being orderable. You can also, in an ordered group, define the absolute value of an element. So if for any A and G, you say the absolute value of A is A if it's positive. If A is negative, then minus A is positive, or it's 0. Sometimes if you have a totally ordered set, a minimum element in the set is just an element which is less than or equal to everything else in the set. And you say a subset is well ordered if every non-empty subset has a minimum element. You say a subset is dual well ordered if every non-empty subset has a maximal element. And there's a very simple, useful lemma that says in a totally ordered set, if two sets are well ordered, then their union is well ordered. And the reason is simply that if you take a non-empty subset of the union, Y, if it's container one or the other, it contains a minimal element. Otherwise, it splits into a union of these two sets. This is a non-empty subset of the well-ordered set X1. This is a non-empty subset of the well-ordered set X2. Each of them has a minimal element, and the minimum of those two elements, which exists because this is totally ordered, is the minimum for the set. This is really a critical fact in the following context. So I want to describe a very special ordered abelian group. But it turns out it is, if you like, the mother of all abelian group, ordered abelian groups. And that is what Hahn's theorem says. So if you have a totally ordered set, if any set, you look at all real valued functions on the set, that's an additive abelian group. You get two functions, f and g, you add them, f plus g. So we're interested in a certain subgroup of the group of real valued functions on omega. And so if you have any function on omega, the support of the function are all of the elements of omega where the function is non-zero. And we're not going to look at all functions on omega, but only those functions whose support is well ordered. Okay? And I claim this is a subgroup of the group of all real valued functions on omega. It's an additive abelian group. And the reason is very simple. Once you see it, I mean, all these things took me a week to figure out, but that's all right, because I'm slow. So, so if you take two functions f and g in this set, their supports are well ordered. And the union of two well ordered sets is well ordered by the previous lemma. If f is not the same as g, that is, if f of x is different from g of x, then it can't be the case that both f of x and g of x are 0, because then they would be equal. So at least one of, so x is either in the support of f or the support of g, which means that the support of f minus g, that's all omega, where f of omega is different from g of omega, is a subset of the support of f union the support of g. This is well ordered, so this is well ordered. So f minus g is in this set. So this is a group. This is a group. And there is a very beautiful way to put a lexicographic order on, I think this should have been r to the omega. I'm not sure why that's there. So that f be a non-zero function.
Mel, what your slide says is you're going to generalize, things from n to the d to r omega. So what you wrote is fine.
Oh, sorry. Thank you. Yes, that's true.
Yeah.
You are correct. Thank you. So that F be a non-zero function in R omega. So the support is non-zero, so the support is non-empty. It's well ordered, so it has a minimum alpha. And we say F is positive if F of alpha is positive, and F of negative if F of alpha is negative. Then this is a total order on this group, and R omega is an ordered abelian group. So this is exactly the lexicographic ordering on n0 to the d, where omega is just a set of integers 1 to n, ordered by 1 less than 2 less than 3, and so forth. And I gave a proof, but that's okay. So that's a lexicographically ordered set. Now, in some sense, every ordered abelian group sits inside this group. So in what way? So let G be any ordered abelian group. You might say, by the way, whatever happened to Schnellmann density? I'll get back to that. I'll get back to that. So, so let X and Y be in the group, and X and Y are positive. So we say that this X and Y satisfy the Archimedean property, say X twiddle Y, means X is less than My. That is, if you add Y to itself enough times, it's bigger than X. And if you add X to itself enough times, it's bigger than Y. So like the positive real numbers have this property, right? And so, but this is an equivalence relation. So two elements are equivalent if they satisfy this property. So you have the set of the Archimedean equivalence classes. So you have the Archimedean equivalence class of X. Now, see, I'm starting with the group G. I want to show that this group sits inside or embeds in a nice way into this very special group, omega to the R, of R to the omega, functions from omega to R with compact support. So from the group G, I have to construct a totally ordered set. So omega is going to be the set of the Archimedean equivalence classes of the group G. And well, you might be like, if you had the reals, there's only one equivalence class, because for the reals, you know, for any X and Y, they're equivalent. So omega could be just a singleton. In that case, what is called Hahn's embedding theorem is a generalization of a previously known theorem of Hilbert. But anyway, omega is the set of equivalence classes. And how do we order it? So we say that an element in the group G dominates an element X if no matter how many times you add X to itself, it's always less than Y, right? I mean, you might say that's kind of weird, but what can we do if the world is weird sometimes?
Actually, I mean, infinitesimals and ordinary real numbers, right? You add up an infinitesimal to itself as many times as you want. You never pass any positive number, ordinary real. That is
correct, right? So it can happen. It is weird. So we have two examples of weirdness in the world right now. This is one, and Wallace is shown. All right, doesn't matter. So if you have two Archimedean equivalence classes, we say one is less than the other if Y dominates X. So so this is a way to order, and in fact, totally order the set omega. I mean, all of this needs to be proved, but it's, you know, you sit down and you work it out. I could say you look it up, but I have no idea where you look this stuff up. But okay. So there is a great theorem due to Hahn. It was from around 1910 or so. Again, this is the same Hahn as the Hahn-Banach theorem. It says that every ordered abelian group is order isomorphic to a subgroup of the lexicographically ordered group R to the omega. So from the group G, you construct, by looking at these Archimedean equivalence classes, a totally ordered set omega. You look at all the functions from real value functions on omega whose support is well ordered, and your group G embeds, that is isomorphically and order preserving, embeds into this. So this is sort of like the master group for ordered abelian groups.
Is there any tricky set theory hiding here? I mean, at the very least,
oh, absolutely. And I mentioned this to choice. David Ross, who wrote back something like, there are questions whether this is equivalent to Zorn's lemma, the axiom of choice, whatever. It's Hahn's original proof. There was a paper that was 50 pages long. The first 20 pages were a preliminary, and then the actual proof was 30 pages. So you have two choices: learn German and read his paper, or in the 1950s, there were two guys, Hausner and Wendell, who proved a version of this in 2 pages, not for abelian groups, but for ordered vector spaces.
Yeah, that just went into the chat.
Ordered vector spaces.
That just, someone just put that in the chat. Clifford, you're aware?
Sorry?
Someone just put that into the chat, a file with the information on that.
Okay.
Ordered vector spaces.
Right. And then a guy named Clifford showed that you can modify this paper of Hausner and Wendell and prove Hahn's theorem. So there's a proof now, which probably is like when you write it all out. The published papers are maybe 10 pages. When you write it out, it's maybe 15 pages or something.
There's a hidden quantifier, right?
Sorry?
There's a hidden quantifier in your statement, right? It's for some omega.
No, for the particular omega constructed from the group by the method of looking at equivalence classes of elements with respect to the Archimedean property. So the group, from the group, you use this Archimedean property to construct the totally ordered set omega, and that's the omega that's here. So I should have said maybe every ordered group G is isomorphic to this omega. Maybe I should have called this omega sub G. So you see exactly how this omega is constructed from the group G. Now, again, this is all highly non-constructive. I mean, you use well ordering on all this stuff that set theorists worry about, but I don't. You know, I just don't. But I mean, it's sort of like, you know, some people worry about the real numbers. And I remember once talking with Saul Kripke, who unfortunately died a couple of years ago. And Kripke said to me, you know, saying about, you worry so much about the real numbers. And I said, I don't. I mean, so some people worry about what, you know, set theoretic axioms. Or, in any case, it's perfectly good for me. Okay. So now, okay. So so I claim I'm about to write down some ridiculous, complicated lemma, which implies, among other things, that Schneermann's inequality holds for lattice points, but in fact implies that Schneermann's inequality holds for very general classes of ordered abelian groups. So it's so I apologize for this, but okay. So for this, I actually have a proof. This is, if you like, my lemma, because I don't know where it comes. I mean, this wasn't in what I found, but it was sort of like extracted from it. So you have an additive abelian group G and a subset U of G, which is downward closed with respect to some partial order on G. And we have a set, actually, I use U here. I should have used J because in the theorem, this is one of those test sets for the definition of Snell density. So use a subset of G that is downward closed with respect to some partial order. And B is a dual well-ordered subset of G. That means every finite non-empty subset, every non-empty subset of B contains the largest element. And in this set B, everything is positive, greater than 0. The set U is not completely contained in B. So the complement, U minus B, is non-empty. And for every V in this set, there's some element in B which is smaller than V. Now, you might say, where do these absurd conditions come from? I have no idea. I wrote them down. And the conclusion is that this set V, which is the complement of B and U, is partitioned into pairwise disjoint non-empty sets. And there's an element Bj in B where if I look at Vj minus Bj, right, I'm sitting in a group, so I'm allowed to subtract. So this set is downward closed with respect to this partial order. And so if in due course I post some of this on archive, there will be a proof. The only way to understand where this comes from is if you go back to the proof of Schneermann's theorem in 1930 and look at what he did for sets of integers. In some sense, what he did is generalized here, right? But that's all I can say. And my next to last slide, I think. I know this is part of it. Okay. So here's a theorem. Take this with a grain of salt, if you like. So G is an additive abelian group. There's a partial order on G. And there is also a total order on G that extends the partial order. With respect to the partial order, there is a decomposition of G into positive and negative elements. And with respect to the total order, this is a totally ordered group. So if you think of the non-negative lattice points, with respect to lexicographic order, it's totally ordered. With respect to that coordinate-wise order, it's partially ordered. I'm not sure about this decomposition. I thought it probably should be down in that. It's partially ordered, but it still is a partially ordered group in the sense that if A is less than or equal to B, then A plus C is less than or equal to B plus C. And we let J be any set of non-empty finite subsets of these positive elements. So if you think of G as the lattice points, this is like the non-negative lattice points minus the origin. So there's a non-empty collection of finite subsets of S plus that are downward closed with respect to the partial order. If you take A and B subsets of think of this as the non-negative lattice points with 0 in A and 0 in B. And so the Schneermann density is always defined. It's not like asymptotic density where you have the limit and the limit may or may not exist. Every set down to below has an infinite. So there's a Schneermann density for A with respect to this collection of sets J. There's a Schneermann density of B with respect to the collection of sets J, and we have Schneermann's inequality. Right?
We were getting a question in the chat, which I think is what you really want for finite and downward closed. You want it to be closed as long as it's positive. You don't want to get all the negatives suddenly.
So S plus. So these are non-empty subsets of S plus.
Of
That's
S
only
plus,
the non-negative lattice points.
And that's what allows us to take to say that, you know, we're still finite.
Yes. Yeah.
Right. Sure. Okay.
Okay. So. Okay. So this is a theorem, which, I mean, I should put theorem in quotes because I'm not sure to what I would like to be able to say is that this is true for all torsion-free additive abelian groups. That would be like a nice result. So it's not just the integers, not just the lattice points, every torsion-free additive abelian group. And why is that true? Because every such group is contained in one of those lexicographically ordered groups constructed by Hahn, and this theorem should apply to that.
You don't need some sort of discreteness condition here? Nothing? I mean, infinite things can get, you know, messy very fast. You really want to deal with finiteness here somehow. And I mean, even just saying you're in S plus, as long as we're discrete and it's well behaved, like lattice points, and we're okay. But if it's not discrete.
Yeah, so that's a good question. I mean, it really depends on when a proof is written down, what makes the proof go through. Right? And then after you have a proof, you write down the theorem that you prove.
And so you'll need to see which conditions really show up, and then according to that, you might need to add more conditions to your theorem.
Where this comes from is when I found the proof for lattice points in my notes and looked at it for a while. I realized it has nothing to do with the lattice points. It has to do with the existence of a partial order and a total order that extends the partial order. And I'm not sure what else, but you know, these downward closed sets, and that's where, I mean, so then I'm trying to sort of prove this. I just want to say what is true. That's really the question. The proof for lattice points is fine, but wherever I use anything having to do with lattice points in my original proof, I could take it out and somehow write it in kind of an order theoretic way.
You're going to give us the proof for lattice points at some point, or you're hoping to? Are you planning to give us the proof for lattice points? I mean, not necessarily today, but at some point.
Well, I'm planning to give a proof of this, and as the corollary, just say let G be the non-negative lattice points.
Sure, but you know, I mean, suppose this takes you a little longer than you expect.
Then I will make available my proof for lattice points. But I mean, the proof for lattice points was only sitting on my computer for 10 years. So what's the rush?
Well,
I mean, the world is not waiting with bated breath to see these results. Heavy stuff. Hi, Ali.
Hi, Mel.
So do you know why people in microeconomics write papers about utility functions or something? And these kinds
they
of
like, Arthur Paul is also here. They like to represent binary relations in terms of functionals of various kinds and the properties of those functionals. And in games also, under binary relations of a group of people in society, they want to represent functions which game theorists can use. but there is more to it than that. I'm mulling over it. I will write to you.
Okay.
Paul, you have anything?
I don't want to. Yes, Paul?
Yeah, I mean, it's an extension of the real valued version. Holder's theorem, right? So Holder's theorem is really important in economics, right? You use it, to get real valued utilities. Hahn's embedding theorem can be seen as an extension of this. Yeah, I mean, that's about, there's to it, I think economists are not in the business of doing interesting mathematics, but of modeling things that are interesting, I suppose. And under what conditions you can obtain, or what rationality conditions or whatever you can obtain representability of some sort. I mean, the nice thing about these Hahn, these Hahn fields or Hahn groups, right? You can sort of think of them as power series, right? Like formal power series, and those are, easy to work with in some ways, right? There was stuff on like on continuous rings of functions, right? So going back really far, right, or something. I'll provide a reference in a second, right? Which is really related to this, but I don't know as much about it as I ought to. It's old stuff, I think.
So Mel, I'm hearing the seminar talk today as saying that Schnirelmann's theorem isn't really number theory. It's about these ordered groups, and numbers are just an example. What do you think that Mann's theorem is in that same category?
So, so the alternative point of view is that all this order stuff is part of number theory, and I mean, you might say, well, everything is number theory, though. No, so the next question would be, if any of this is correct, is whether the stronger inequality of Mann and the even stronger inequality of Freeman-Dyson also, in some sense, just depend on the order structure of things. Life is short, and there's always stuff to do, and I would rather. But then in some sense, is a natural next question to look at.
You have to leave something for the students to do.
Sure.
So you prove this result. Can you give some intuition for why it's true?
I'm sorry, my phone keeps ringing. So what was the question?
Can you give some idea, some idea why it's true, the result that you displayed and then took away really quickly?
Oh, you mean that lemma?
Yeah.
Why is it true? Well,
The last, in particular, the part that comes after the end.
so there really is a kind of abstraction of the lemma, specifically in the case of non-negative lattice points.
Aye.
And so that obviously I wrote down 10 years ago, but I don't even know that it was my proof. I mean, someone might have told me it, or I might have seen it somewhere in some obscure place. So I don't claim any ownership or originality with respect to that. Fortunately, I have a very old computer, because it's very old, but it's old enough that it has a lot of memory. So I once went to my local Apple store and I said, I want to replace this. And they said, I want to buy a new computer to replace this. And they said, no, you don't, because we don't make them as good anymore. And if it still works, keep using it. So I ended up buying actually another Apple to use when I travel, because this one is too important to take anywhere. But yeah, I mean, as Kevin knows, I'm always writing stuff down, and then it just gets buried somewhere. It doesn't get erased. But so 10 or 15 years ago, I started to write up this book on density, additive number theory and density, and So this was actually part of the chapter, or part of the draft of a chapter on Schnirelmann density. That's where I found it. And I will say that it took me a long time, and I still haven't succeeded yet, in understanding even just the statement of Hahn's embedding theorem. So, you know, it just I can state it formally, but just to get a sense of why these lexicographically defined groups based on these real value functions on a totally ordered set with compact support, why in some sense those are the master ordered abelian groups. I did see somewhere on the internet someone, as part of some program in algebraic geometry, giving a long detailed proof of Hahn's theorem. And other than maybe because it's connected with, you know, sums of lattice points and toric varieties, I don't know why it would have fit into some algebraic geometry program. But it really is an interesting theorem. I mean, unfortunately, mathematics is filled with almost forgotten, really interesting theorems. And, you know, that's the whole story. You know, there are people who are disciplined who can like focus on something and do it. I'm undisciplined, so I get interested in something and distracted from what else I should be doing. Like, this is really kind of a distraction, but it is very interesting. And I am very happy to have come across this Hahn's embedding theorem. And I remember I looked at ordered groups a very long time ago, and there was some guy named Cohen who somehow in World War II escaped from Europe and got to India. And he wrote some of the original papers on ordered groups that were published in the Journal of the Indian Math Society. But like something like the middle of World War II. I mean, he was lucky he got to India, but he was able to do some math there. So, and I remember at the time I could actually track down the papers, and I probably should do it again. But yeah. That was really the origin of a lot of this work.
Thank you very much.
Will you be averse to circulating your slides, Mel?
Averse to what?
To circulating your slides?
I have no objection. I'd be embarrassed to, but I can.
No,
send
something
them.
to mull over, because you know you went very fast for me. I'm just a mere economist. So with a paper and pencil, I would like to put them to the.
Well, I will send them to you or anyone else who wants them. But
Okay, I would be grateful.
I wouldn't post them on, you know.
No,
website
just
everywhere, 'cause
just
they're really
send
not
yeah.
any good. I mean, they're not good enough, if you like.
Thank you.
And I really hope that within a couple of weeks I will, you know, actually write up something with details complete and actually have, you know, something I could put on archive. That's it.
So Mel, as I emailed you, there's also apparently a way of looking at the embedding theorem using surreal numbers. Now, I know just about nothing about surreal numbers, but a lot of the mathematicians in the early 20th century, late 19th century were really interested in things like orders on sequences of real numbers. Or more generally, just orders on functions from the reals to the reals. And you can order functions from the reals to the reals by, you know, one is bigger than or equal to the other if it's bigger in the limit as x goes to infinity. And it's known since the 70s that if you look at for example, the exponential polynomials, I'm getting to a point here, the exponential polynomials, that ordering is actually a well ordering. That's quite an interesting theorem. And it's been a conjecture since the 50s as to what the order type of that well ordering is. Anyway, the reason I bring all this up is that there's been some recent progress in that the old problem of what the order type of the ordering is due to Skolem. But there's been some progress in this question of understanding the order type of this set of functions. And the progress apparently also uses serial numbers. There's a model theorist in Italy who's got his students working on this, and they've made some really nice progress on it. I had a student lecturing to me about this stuff, and I about half understood what he was saying. But in any event, I don't know really how this relates to the Hahn theorem, except that, as I say, there also apparently are ways of dealing with this using serial numbers. Apparently, it's a nice environment for looking at lots of well orderings.
Yeah, so I know nothing about serial numbers, but I have noticed that in the literature on the Hahn embedding theorem, there are references to papers with the word surreal in the title.
I mean, years ago, I tried to see if I could come up with a proof of it non-standardly. And the problem, yeah.
Oh,
and the
wow.
problem is
Oh, you're ahead of the game.
I spent a few days on it, and the problem is that non-standard analysis is just atrocious for dealing with well-ordered sets. I mean, even the simple question, right? It should be possible to well order, let's just say the reals. It should be possible to well order the reals using non-standard analysis, because non-standard analysis is equivalent to the axiom of choice. And there's no sort of natural way to do it that I've ever nobody's ever, I don't think, looked at it formally, but when I've thought about it, you just always get led back to the usual proof using Zorn's lemma or something. I mean, there's no sort of essentially non-standard way of doing that. Now, I don't know about the real early literature. This is the sort of thing that somebody really should have been thinking about in the late 60s, early 70s, when people were sort of exploring non-standard stuff. But I wasn't around. Now, I know Ali was for not maybe the earliest part of it, but for earlier than I was. And I don't know if you remember any talks at any of those early meetings on this kind of thing.
Oh, Ross, I was naive. I was coming from economics. Even if I heard them, it would go over me. Yes, I did attend. There was a conference which Keith Stroyan organized in Iowa, which I still remember the invitation. It said, "Dear friend of infinitesimal quantities." And then it followed with the invitation to come. But yeah, I used to go, but I just wanted applications of some simple, of lobe things.
Yeah. I mean, these things about, if you have a non-Archimedean ordered group, and so you get things group into sort of galaxies, I think was an early term for these things.
I remember
stuff that people have looked at a lot over the years, but how, in very old years, but how this would relate to the proof of the Hahn theorem, I don't know, but it's interesting, because it is an interesting theorem, little standalone result.
Is anyone interested in these questions? These embedding questions for ordered abelian groups?
I am.
I am too. That's why I'm here.
In the economics world.
Well, yeah, you have to wait for that.
Doing trivial things, yeah.
Actually, at Hopkins, you're close to Washington. You ever hear of this guy, Brian Deese, who was the head of Biden's Council of Economic Advisors?
No, I have not, man. I have not. But then again, I feel embarrassed because with Ross I say it goes over my head, and to you now I will say, I don't follow these economic policy types. So you guys can ask, what do you do?
No, what I just found really interesting as a sign of my old age. So this guy, Brian Deese, whoever it is, got this extremely high level job in the White House as head of
Yeah.
economic policy. I knew him when he was 1 month old.
Oh, really?
I mean, I knew his father. His father's a professor at Boston College at poli-sci, and I was in Cambridge for the year, and I was around when he was born. So, so somehow he went from being 1 month old to running economic policy for the United States government. Pretty impressive. Who would have guessed when you first saw this kid? All right, all. Good to see everyone, and let's see. Same time, same place next week.
Thank you very much, Mel.
Thank
you
you
very
thank
much.
you, Thank you very much. Thank you.
Bye.
Good to see
Thank
you,
you.
Ron.
You.
So, Mel.